Good morning. So we're going to be talking a little bit about the normal and tangential coordinate systems and mainly the ways to find and the different forces that you'll experience in this coordinate system. So as this coordinate system suggests, there is the normal and the tangential directions. So for a minute, let's just imagine that we're spinning a ball around, and this ball is on a string, and this is its path, right? So we're spinning the ball this way around the string. Okay, so it has the direction that way. At any point during this swinging, this ball is going to experience forces in two different directions. So it is going to experience forces in its tangential direction, which are tangent to its curve, and more specifically the exact point that it is on in that arc that it's spinning around in. And this is going to be the tangential direction. So we'll go to unit vector, tangential. Okay. And then the other force is the one that people tend to have a hard time conceptualizing, but once it gets kind of shown to them, it makes a lot of sense. So this is going to be the normal force. However, people tend to get it confused with something that they've heard called a centrifugal force. People tend to think that as you spin something around like this, it has a force pointed this way, is what they'd say centrifugal force. Just because that's kind of what you would feel, right? But that's not actually true. What you're feeling is this force in the normal direction. So unit vector, the normal direction is what you're actually feeling, is the normal force on the string, or on, if this is a roller coaster, on the track of the roller coaster pushing in towards the center of the curve. So there isn't actually any force pointed off this way. There's only this tangential force, which would be any accelerations with the velocity of this ball that we're spinning, and then the forces normal keeping it along that arc. So let's look into the acceleration forces, because the accelerations will help to describe the different velocities, which will help describe the vectors, or the forces. So we're going to look into acceleration. So acceleration has two different completely separate, not completely separate, but separate parts. So there's acceleration, as you may guess, in the tangential direction, and then that's added to the acceleration in the normal direction. So as it's moving, right, it has its tangential direction. And this is, if you cut the string, that's the path it wants to go on. So it wants to go on this path, same speed, same direction along this path. So in order to make it go on an arc, something has to act upon it, right? Something has to keep it along this arc. So there has to be an acceleration in the normal direction. At every single point, it has to be accelerating into the normal direction so that it doesn't continue along a straight path. And then if it wants to speed up or slow down, then there has to be an acceleration in the tangential direction. So acceleration in the tangential direction is equal to the mass of the object times any change in speeds. Can also be written as m v dv over ds, which is just mass times velocity, and then change in velocity over change in position. Acceleration in the normal direction is equal to mass times velocity squared over rho. What's that rho? So this rho is called the radius of curvature. Okay, and there's two ways to find it. So if you're on a circle, it's just equal to the radius. So like over here, we're going to talk about this diagram a little later, but right, you're on a circle, rho is just the radius of the circle. Obviously the radius of curvature, radius of the circle. But if you're not in a circle, but you're on a curve, like if you're out in this area, and you know that that curve is a function of y, or is y a function of x, then it is going to be equal to 1 plus y prime squared, square the top, or multiply the top to 3/2, and then over y double prime. And this is if you're given y as a function of x. So that's what rho is, right? So it's your mass times your velocity squared over whatever arc you're on is going to dictate what kind of acceleration you're going to need. Now let's look at the different forces. Okay, so in the tangential direction, you're going to have all of the forces, so the sum of all of the forces that aren't because of the ball doing whatever motion it needs to do. So this is going to be if you have a bar attached at a pin or something, right? You have a bar here. If there's any force in the tangential direction, like say you have a force here, or it's getting hit by something or whatnot, those are going to be any sort of forces tangential direction. So you just sum all of those forces up on one side, and then that is equal to acceleration in the tangential direction. So m v dot or mv dv over ds. And excuse me, actually, in these accelerations, there's no mass in these accelerations. It is just, for tangential, it's just the change in velocity, and then for normal, it's v squared over rho. Over here is where we stick in the masses, okay? So then in the normal direction, you have your force in the normal direction. So in this pin, say you had a weight down here, right? You got mass, gravity, and then your force in the normal direction right here. Okay, so force in the normal direction is equal times the mass of whatever you're dealing with times v squared over rho. This is also mass, acceleration in the normal. This is mass, acceleration in the tangential. Right, so that's the different forces and kind of how you would find what forces in the normal and tangential direction. So next I want to do a kind of simple example just to help learn the theory behind it, and it's something I think is kind of interesting because if you've been to a roller coaster, you'll be able to understand why the mass of the roller coaster doesn't matter. So you can have roller coasters of different speed or different weights, and it will never change the path of the roller coaster, right? So in this problem, we want to find what the slowest speed the car can travel and not fall. So we're going to say that the mass of the car is 40 kilograms. We're going to say the radius of, let's say it's on a loop, right? We're going to say the radius of this loop is 20 meters. So we're trying to find what velocity. So we're trying to find the velocity this thing's moving at to keep it up there. So let's draw just a little diagram of just the car. Also, free body diagram, just the car. What forces are acting on it? So we're going to say that it has a constant speed. So V is constant, which means that V dot is equal to 0. So what are the forces? Well, it has a mass, right? So mass times gravity. And then there's the force of the track pushing on the car. So there's a force in the normal direction of the track pushing on the car. So there are no other forces acting on it. Okay, so let's do our force equations. So forces in the tangential, there aren't any, but let's find forces in the tangential. They're equal to mass times change in velocity. There's no change in velocity, so that equals 0. So those all equal 0. Forces in the normal direction is going to be mass v squared over rho. Forces in the normal direction, you have n plus your mg is equal to mass v squared over rho. So our normal force is going to be 0, because we're trying to find the slowest the car can be traveling to get that normal force down to 0. Because if your normal force is at 0, that's the slowest you can be going. If your normal force exceeds 0, that means you're being pressed against the track, and if it gets any lower than 0, it means that you fell off the track. So your normal force equals 0, that's the slowest that you're going to be able to go in order to stay on the track upside down. So normal force drops out. You can cancel masses on each side, and you end up with G is equal to